In the previous video, we have seen the theorem of parallel axis. Now we will move on to the theorem of perpendicular axis. So first we will go through the statement. It states that the moment of inertia along an axis perpendicular to the plane of lamina is equals to the sum of moment of inertia of the lamina about two mutually perpendicular axes in the plane of lamina and intersecting each other at that point from where the perpendicular axis passes through the lamina. So, lamina. What is lamina? Lamina is kind of a body, like a plate-like body, or we can say paper. Paper is a lamina. So we can take a lamina as a paper. A thin plate, we can say, is a type of lamina. So this is our lamina, and a perpendicular axis is passing through this lamina, and we can say take it as a z axis. It states that the moment of inertia along an axis perpendicular to the plane of lamina is Iz. Moment of inertia along the perpendicular axis is equals to the sum of moment of inertia of lamina about two mutually perpendicular axes in the plane of lamina. Suppose there are two axes which are mutually perpendicular to each other, and they are lying in the plane of lamina, x and y. So to the sum of moment of inertia of the lamina about two mutually perpendicular axes in the plane of lamina and intersecting each other at that point from where the perpendicular axis passes through the lamina. And these both axes are mutually perpendicular to each other, and they are intersecting the perpendicular axis which is passing through the lamina. So basically all the three axes are intersecting at a single point, and moment of inertia of both the axes, sum of moment of inertia of both the axes is Ix plus Iy, and it is equals to the moment of inertia of along Iz. This is our theorem. A very simple theorem. Moment of inertia along an axis perpendicular to the plane of lamina is equals to the moment of inertia of lamina about two mutually perpendicular axes in the plane of lamina and intersecting at each other at that point from where the perpendicular axis passes through the lamina. Now we'll see the proof of this theorem. First we are considering a lamina and a perpendicular axis is passing through this lamina. Suppose this lamina is made up of n particles, and each particles are carrying mass m1, m2, m3 up to mn. So first we will write let us consider a lamina consisting of n particles of masses m1, m2, m3 up to mn. And also we will consider this masses having perpendicular distances from this z-axis r1, r2, r3 and up to rn. So we can write, let r1, r2, r3 up to rn be the perpendicular distances from the z-axis which is passing perpendicular to the lamina. Now if we take x and y axis in the plane of lamina and they are mutually perpendicular to each other, and also all the three axes are intersecting at a single point, then if we take a mass on the lamina m1, then and also this is at perpendicular distance r1 from the z-axis, see this is our z-axis and this is x-axis and this is y-axis, and this particle is lying here m1. So this distance is x1 and this distance is y1. So x1, y1 are the perpendicular distance from the x-axis and y-axis. So we can write here, if x1, y1, x2, y2, x3, y3 up to xn, yn are the perpendicular distances from x and y axis, then see, this is our x-axis and this was our y-axis, and this is distance r. So this is x1 and this is y1. So this line is parallel to this line, so it is also y1. So from Pythagoras theorem, we can say that r1 square is equals to x1 square plus y1 square. Similarly, for all the particles, we can write r2 square is equals to x2 square plus y2 square up to rn square is equals to xn square plus yn square. And now we put all these equations simultaneously as first equation. Now what we'll do next is, for each particle, the moment of inertia about z-axis of this lamina, for each particle, the moment of inertia about this axis can be written as m1 r1 square, and for all the particles or whole lamina, we can write moment of inertia along z-axis m1 r1 square plus m2 r2 square, summation of moment of inertia for all the particles. This is our equation second. So we'll use this equation in this equation. So using equation first in equation second, so what we'll get? What we will get, Iz is equals to m1 r1 square x1 square plus y1 square plus m2 x2 square plus y2 square up to so on. Mn xn square plus yn square. Now Iz is equals to m1 x1 square plus m1 y2 square from here m1 x1 square, and from the next term m2 x2 square, and from the third term m3 x3 square up to mn xn square. And from the second and from the y2, from all the terms m1 y1 square plus m2 y2 square plus up to mn yn square. So from here we can see that this whole thing is the moment of inertia along x-axis, and this thing will be the moment of inertia for along y-axis. So simply we can write it as Iz is equals to Ix plus Iy. This is our